virtual environment. So thank you for being a part of that. Thank you again for joining us. And to introduce today's speaker, I will pass the mic on to the series convener, Sudarshana Mukhopadhyay. And with that, thank you very much.
Thank you, Julia, for that introduction. Once again, thank you all for joining us today. As Julia mentioned, we'll be monitoring the Q&A section throughout the seminar and save the questions for the end. So I'm really pleased to introduce our speaker today. Our speaker is Mike Johnson. Mike is a water resources data scientist as Linker Technologies affiliated with NWM. He's also a PhD candidate at UC Santa Barbara. He has worked extensively with members of the USGS on NHD+, the Network Linked Data Index, the National Water Model, and so on. So without further ado, I'll turn it over to Mike.
Awesome, thanks. Let me get this shared. I'll put it in present mode. Cool, well, thanks for the introduction. Since it's week of Thanksgiving, I'll go through this briefly and hopefully have some good time at the end for some questions. So today, general topic is digital connectivity. And the focus that we're really going to look at is enabling feature level flood forecasting and risk assessment. And this is going to be cross scale at the building level. Like, is my house flooded, all the way up to CONUS. As mentioned, I work for Linker Technologies, and the work that's being presented is funded through the UFOKN, or the Urban Flooding Open Knowledge Network, which is an award at the University of Cincinnati. All right. So to get us started, I just kind of want to have an analogy that we can have in the back of our minds as we're going through some of the content today. And the network that I want to talk about in our everyday lives is just the road network and how we interact with it through mapping platforms like Google Maps. So here's an example we're probably all familiar with. We want to go from one place to another, in this case, maybe Roland Moore Park in Fort Collins to Estes Park. And if we put this into Google Maps, we get some kind of information about the network, different ways to get from one point to another, but it's all based on this underlying general network. It's really nice that Google Maps can tell us things about behavior on the network. For example, here we're seeing things like what are the current traffic conditions. If we take one route versus the other, how long is it going to take based on those different routing conditions? And so now we're looking at not only how we might interact with the network, but also current properties of the network and how we might deal with them. And these properties are pretty dynamic in that they can change through time, or we can look at long historic, I guess, records or common traits. Another thing that Google Maps or these road network type applications have really had to take into account is how do we standardize data, the fact that we have these lines on the map with culture and generally how we refer to these things. And one example here, if you take a street in downtown Fort Collins, right, at some zoom level, it's called Highway 287. If you zoom in, you'll notice that at some scale, north of Mountain Avenue, they call it North College, and south of East Mountain, they call it South College. So there needs to be some way that we can reconcile these different type things together to know that Highway 287 is the same thing as North College, is the same thing as South College, depending on the scale and perspective that you're interested in. And so why has Google Maps and this road network idea become so prevalent in our lives? So many of us are using it. And largely it's because many of us take many trips. Americans take 1.1 billion trips a day. And that's for every individual in the US. That's 411 billion trips per year, 1,500 trips per person, et cetera. All these numbers just point to the fact that we really need to know how our behavior with the road network really translates into our day-to-day lives. And the result of this is when we provide a product that can kind of describe behavior on a network, and a network that people are intimately familiar with, you get things like Google Maps has had 23 million downloads in 2020 and 154 million monthly users. But the network we want to talk today that shares a lot of the same characteristics as those we were looking at before is the river network. So instead of looking at the roads, we're looking at rivers, and instead of looking for things like coffee shops and gas stations along the network, we might be interested in things like gauges and dams and bridges and all those other nice infrastructural features. And so far in this series, we've seen different talks about these types of things. Dave Blodgett talked about the river network and how we identify them and name them, his main stems work. We've seen digital connectivity between gauges and dams, I think last week. And in the first week, Internet of Water talked about how they are indexing and making things like stream gauges and dams and bridges more easily discoverable with persistent identifiers that can be found through more internet schematics rather than common just language. And to point out a few of these commonalities across these, when we look at main stems, it's really trying to identify with or deal with this data that we saw on the road network about how scale, names, and culture can have different effects on the pure digital data. So main stems works to have common identifiers across scale, across data sets, across vintages. And that's the work that Dave mentioned. So that really gives us this underlying network that we can do operations and things on. Got a little lag there. Cool. And in the same way that if you put a route into Google Maps, you might ask about find hotels between Santa Barbara and San Luis Obispo, or find gas stations between Fort Collins and Estes Park. GeoConnects is providing some of the similar capabilities specifically for water-related information. So you can see in GeoConnects, they have things like HUC2's index, HUC4, 6's, 8's, 10's, national aquifers, gauges, different states and counties, and they're providing persistent identifiers for these. For that, web searches and web engines can go out and find information somewhat in a similar way that you might be more familiar with in a mapping context. There are certain platforms out there, the National Water Model is one of them, that provides something kind of analogous to being able to look at local traffic conditions on the network. So in the same way you might want to know that there is congestion along Valmont Road in Boulder, you might use the National Water Model or particular aspects of different hydrologic models to understand conditions on the network. And so together we kind of set the stage that we have the ability now to have interfaces like Google Maps more focused on the river network and how we relate to water conditions. But the premise of this talk and the work that I've been working on for the last year or so is that the way that people want to understand these networks are very different. The way they want to understand the road network is different than how they want to understand the river network. And when people are looking at the roads, they want to know about how things on the network impact them while they're specifically on the network. So how do they get from one point to another? That point might be a gas station that they have to discover through some sort of linked data mechanism, but they're still interested about things on the network. When we talk about rivers, people in general want to know about things, how things on the network impact them while being off the network. And the case studies that we'll look at about today are things like, will my home flood and will my neighborhood experience flooding? So two different scales, but interested in how behaviors of the network impact places and things important to them. And so when we bring up the idea of digital connectivity, or where we're taking this analogy, is that we want to connect our material, social, and physical world to the dynamics of the river system. And Water and GeoConnects has done a very good job of integrating kind of the physical hydrologic world to this river network. But we're interested more in kind of the urban multiplex, or how these material, physical, and social things about us actually integrate with this network and the behavior of the network. And so generally we think the impacts happen at locations of interest, right? So we're interested about flooding on a road, we're interested about flooding at a house, we're interested about flooding at a power station. And a lot of open source data efforts have worked to create inventories of these different properties, right? So we have building footprints that could come from OpenStreetMap, OpenAddress, bridges from the National Bridge Inventory, roads could come from OpenStreetMap or Tiger, power stations come from Pacific Northwest Lab or the Department of Homeland Security, dams can come from the Army Corps, and et cetera, right? There's a lot of information out there about locations that we might be interested in with respect to flooding. In general, all of these different spatial features can be boiled down to this more simple idea of just points on a map. The challenge generally, though, is that these open data sets document different parts of this urban multiplex, right? OpenStreetMap tries to collect everything through really high quality controlled user inputs. Microsoft Building only is interested in building footprints taken from an artificial intelligence image processing technique. Open Addresses is only interested in addresses reported from governments. Army Corps National Dam Inventory is, of course, only interested in dams. So there needs to be a way that we bring all of these different features together in kind of a homogeneous way. So some of the first challenges that we've experienced with this is how do we integrate these different data sets? And one of the more challenging ones has been on the building level. Right, and here is a zoom into downtown Wilmington, where you can see that we brought together data from OpenAddress, Microsoft, OpenStreetMaps. The blue dots that you see are those that are defined in OpenStreetMap, Microsoft Buildings, and OpenAddress. So near the city center, all of these data sets are generally capturing these entities. We have high confidence that these features are what they say they are and are where they are, or where they say they are. But then you can see that there's different patches that different data sets do better at collecting. The brown circles here, we get nice information from OpenAddress telling us what the address of that location is, but the address has to be inferred, or the location is inferred based on whatever they provide. In different places, then you can see different combinations of these features, right? When you see purple dots here, those are those that only OpenStreetMap and Microsoft Building caught, and so on. Takeaway from this, it's not so much the focus of this particular talk, but that building an urban multiplex, or something that can truly give us a full understanding of the social material world, requires the integration of a lot of data sets. But fortunately, these data sets are open and free, and when integrated, can provide a pretty holistic picture of the environment that we're interested in. In addition, once we establish these basic points, we have pretty well-established ways of indexing information kind of in the social political realm, right? And so for this, we're using the FIPS codes. These are Federal Information Processing Units that generally just say that first 2 digits of a FIP code belong to the state, second 3 digits belong to a county, remaining 6 belong to a tract and a block group. So as we go through all of these different types of features that we might be interested in with respect to flooding, we can reduce them to locations, integrate them based on their redundancies and overlap in other data sets, ultimately assigning them a location, both in terms of coordinates, but also within the state, county, and tract. State, county, and tract give us nice ways to be able to group, query, and process, and the individual locations themselves are critical for understanding how flooding occurs at that particular location. So going through this, one slide right here. As we've been building out this data set, we're doing it at the county level. We're using those FIP type identifiers, storing and indexing information and processing them at the county and the state level. As we go through different counties, we build out these different data sets, align them, integrate them, make sure they have the right processing code, and we create these cloud native objects that we can store and access using S3 Select, Arrow, Apache, whatever you might want in order to access these S3 buckets. This has all been automated such that each county has a Lambda service that watches for the data sets that make up that county inventory. And anytime there's a change to those or we want to trigger a new build, it will be built automatically. Nice thing about this is that for any county, whether it's in Wyoming, Ohio, North Carolina, changes in the underlying data sets are going to trigger rebuilds of this information that we're using to produce flood forecasts. When we zoom in particular to these, we can see that each county will have a log of what's being built. In this case, this particular county in Ohio has built out buildings, roads, underground storage tanks, power infrastructure. Superfund sites when the screenshot was taken was being built at that time. If you click on any of those, you zoom into the county, you can see where these locations and where these infrastructure actually exist. In all cases where we have the ability to, these are linked out to their native data sets. So if this particular point came from OpenStreetMap, it would be indexed to that OpenStreetMap feature if that's web accessible. And in general, this collection of county-based feature layers provides a foundation for the data-driven interfaces. And so it's an extendable data framework that currently scopes buildings, power, underground storage tanks, and roads. But as we go through time, we'll be able to get more things like bridges, dams, et cetera, as soon as we build the workflows and the reconciliation patterns for them. The key for this, however, is that each of these individual features is forecast ready. When we look at these in aggregate form, this is a 10-meter cell aggregate with counts. It ranges from 0 features in the black to 120 features. We can see that the density of these features ultimately give us quite a dense network that we can produce forecasts on and that we can ask interesting questions about with respect to, is my house flooded? Is the power station flooded? Is my neighborhood flooded? To go from simply a collection of data points, though, however, we need some way to connect them to these forecast models. So when we talk about ERMI, which is this general collection of data that's at a very high fidelity, right, we see that the key is it's forecast ready. In order to be forecast ready, each of those individual points has to be associated with a particular hydrologic reference. And this hydrologic reference is the scheme, or really the glue that's going to hold together the ability to produce these forecasts at the scale and the speed that we want. And one other analogy we're going to use kind of as we go through the rest of it is that we're treating these hydrologic references kind of as an IKEA for flood forecasting. The keys with them are they have to be minimal and compact. They provide directions for user assembly, so the forecasts aren't coming assembled for people to use directly. And these particular hydrologic references are shipped with ERMI features. So hydrologic reference in general is a digital and lightweight description of how any ERMI feature relates to a model forecast. The hydrologic references can be model-centric. For example, you could have a hydrologic reference for the National Water Model, or you could have model-agnostic hydrologic references that would allow you to connect to more general models as long as the model is conformed to the hydrologic reference pattern. So it works either way in that the hydrologic reference can be specifically designed, or models can be built to comply to an existing hydrologic reference. So far, we've tested and somewhat developed acceptable hydrologic reference patterns for 1D, 2D, and 3D models across different structures. It might be an unstructured mesh or a gridded model or even a lumped model. But the hydrologic reference for each of those is a set of directions to tell an ERMI feature how to interact with the forecast from that model. And so within ERMI, then we can have a bunch of different collections of features across different counties that each have a number of particular hydrologic references. Our goal is that every feature is going to have a National Water Model hydrologic reference. For example, if you wanted to know something about your house, you would always be able to pull on the National Water Model reference. But if it was in an area that was more heavily modeled or had other resources available, perhaps this hospital might have a National Water Model hydrologic reference, a city swim model hydrologic reference, and a hydrologic reference to a USGS FIM library. So the amount of data that's available, as long as there's a reference pattern telling ERMI features how to interact with those, we can then pull forecasts directly from them. So moving on today, the reference pattern we're going to talk about is this National Water Model. National Water Model covers CUAHSI. People have different opinions on it. I think it's a great tool for awareness and situational response. So we're going to focus on that one. But it also is going to test and exercise the system for CONA scale platforms. So with respect to the National Water Model hydrologic reference, we're going to make sure that every ERMI feature has this particular hydrologic reference pattern. And the reference pattern for a National Water Model forecast will be defined by a height above nearest drainage, an NHD COM ID, and a rating curve. When you look at the set of these three things, again, an elevation, a COM ID, and a rating curve, this is the IKEA directions, right? It's a minimal and compact set of information that tells us how to interpret a forecast for this particular ERMI feature. It provides directions for user assembly. We're not providing the forecast, just the directions. And it's shipped with ERMI features. So every time you query an ERMI feature and a National Water Model reference pattern, you're getting this set of information with those particular features. Again, not the focus of today, but at a high level, we just want to remember that the way that the National Water Model is forecasting floods based on the height above nearest drainage, is that there is some rating curve that converts a National Water Model stream flow to a particular depth. If the depth in the river is greater than the hand or the height above nearest drainage at a particular feature, then that particular feature is flooded to that value, to the elevation of the river, of the water in the river, minus the elevation of that feature or the hand value. Now, because there's opinions and things floating around about National Water Model, we do want to just preface these again. This is not the particular focus of today. There was an evaluation of integrated National Water Model height above nearest drainage approach. Found in general, it underpredicts inundation in fourth order and lower reaches, but overpredicts in higher order reaches. Stream flow is rarely the limiting factor. Synthetic roughness coefficients that were used were the current weakness, along with the volume of data. So in general, we just want to point to the fact that within this, we've adjusted to some of these and we've made some adoptions and improvements in these particular aspects. We have a machine learning rating curve generation approach that is extendable to engaged basins. When we look at the air produced in them, this upper left is those produced with the global synthetic rating curves. Our network-based approach is really reducing the error that we see in each of the rating curves compared to observed USGS stations. We're not using a single rating curve, but instead we're using a probabilistic and an indexed rating curve to make sure that we are kind of providing a band on the expected flood depths at any particular point and not just a singular value. And by being indexed, we're able to kind of push farther with this idea of an IKEA-based model, in that our minimal and compact set now only requires a hand value and a COM ID. The COM ID provides us a reference to this machine learning driven rating curves that provide probabilistic inundation depths. Let me make sure slides are skipping around. Cool, stay there. Cool, and the last thing that we provide with this is a performance data pipeline. So previously, it took a whole lot of time to download national water model data, crack open each net CDF, pull out the stream flows, pass them through these rating curve lookup tables, and generate national depth forecast or depth tables. We've been able to reduce this down to that on average, it's taken us about 35 seconds to deal with an 18-hour short range forecast. So in total, at the top of each hour, National Water Model releases some forecasts, both medium range and short range. We download them, have some processing steps on top of them to get them into a more performant structure. And then we use our rating curve probabilities to generate depth tables that can be queried directly. And in total, this gives us the capacity to say we have an ERMI feature. It might be your house, it might be a hospital. We have a hydrologic reference that tells us how to look up things across different data sets. And with that, we are able to quickly pull out flood forecasts at that feature level. And again, this goes back to, it's a minimal and compact set of directions for how to put these together. We're not providing the forecast values, but providing the directions for generating them. Every ERMI feature comes with a National Water Model Hydrologic Reference. This reference not only includes the way to get data, but paths to find it. And it comes directly with it if you ask about it from the ERMI data set. By building out these different data sets and focusing on them being cloud optimized rather than dashboard focused, we're able to provide direct digital access to them. So all of those ERMI features that we saw in the original map can be queried in a number of ways. They have S3 select options, Apache Arrow options, VSI 3 through GDAL. Depending how you want to access it and type of end product that you want to deliver, you have different abilities to get that data. How you want to compile and put it together is, of course, on the user end, following that IKEA analogy. But in general, these are ready to build kind of production grade products based on the underlying data warehouse. Some examples that we see here is you might be interested in all of Ohio and impacted features. This goes through and says, take any forecast, short range or medium range, and let's look at buildings and find the percentage of flooded features in each county. This one says in particular, given a set number of points, whether it's a set number of underground storage tanks, a set number of houses, a particular region that you're interested in, find those particular features and extract the time series. And you can build out kind of more production level shiny apps on top of it that provide mapping interfaces, spatial queries and summaries, different types of tables, different types of views of this data. But the idea, again, is that we're building a data warehouse and not a particular set of data to meet the particular answer. So it's on the user end to decide, I want time series, I need to access this data resource in a particular way, or I want a map, so I need to access this data resource in a particular way. To show this at a different kind of scale, if you wanted to build a particular application that worked off of this type of data, we have a set of directions for you. Again, following the IKEA model, we have minimal compact access patterns that are called these hydrologic references. We provide directions for user assembly. Anytime you query ERMI resources, they come with the correct number or the correct hydrologic references that you need. We're adding one more bit to this in that all data is stored in the warehouse. So if you wanted to make a map of North Carolina during, I think this is Hurricane Florence or Irma, I get confused with the hurricanes. This is during a hurricane, so we expect some sort of flooding. You would say something like access all risk points or all ERMI features for a particular state, county, and type. The state that I want is 37, that's the zip code for North Carolina. You would collect the data, you would join that data to the depth table that is also additional resource with directions based on the hydrologic reference. And you would then compute the actual value at each individual point. Remember, you have a hand value and you have a depth value. You need to go across and actually define the depth value at any of those features. Ooh, come on, slide. Lagging, I want the one right there. Awesome. And in this particular example, we can go from making this request, sending this out, and we can bring it into two different types of interfaces, right? One of them can be a tile PNG server. It's nice to look at, but you can't do any particular analytics or data analysis on it. Or you can stream it directly through open layers into a QGIS environment. In both cases, you're getting different views of the data. It depends on what you're interested in, but they're directly hitting the data warehouse. For example, here about how these actually run and the performance of them, we're looking at a state level information, almost 15 million different features. If you run this off local data, so it's sitting on your computer, or you're running your application in the same AWS region as the data is stored, you can look at pulling a state and generating either of these views in about 30 seconds. If you do it directly through an S3 call, so this is saying your data is sitting in Virginia or Ohio, and you're pulling it to Colorado or California, you're looking at about 101 seconds to generate either of these views. But again, the key in the digital connectivity that we want to kind of focus on for today's talk is that the views are generated by others. The access and the patterns and the way that the data is interacted with is specific to ERMs and hydrologic references. Again, just want to focus on specifically that the idea here is not that we can make dashboards. Everybody has dashboards. They want their dashboards to do different things. You can make a career out of building dashboards, even the same dashboards with slight differences. We can do that. We can build dashboards on these things, but the idea really is that to create true digital connectivity, it's really the system underlying it and not one particular view. Any dashboard that you build on top of it, any view that you build on top of it could be considered a one-off to look at individual information based on time and space. So kind of complete this IKEA analogy that I hope not boring you to death with, is that we built a knowledge network based on these ERMI features with hydrologic reference patterns. Reference patterns can range from one being the national water model to as many as you want. You can index flood inundation libraries from USGS, floodplain, any type of platform. You can index specific models like SWIM or HEC-RAS that are existing in that area, or you can call directly on the national water model. We do provide some dashboards. There's one that we saw before, right? These are inspirations. We don't think anybody necessarily wants that particular tile view or that particular county-based aggregate dashboard. But what people really want is customized data pipelines and outputs. And so that's what we're trying to provide with this, is a system that can be accessed in a number of ways and built to meet local needs or even regional needs. And so to tie all this off, let's see, perfect doing well on time is why does this matter? And one of the dings the national water model gets, and we're familiar with it, is that all models are wrong and the scale of their performance can range. But the nice thing with this type of system is that we can start collecting data at a very fine granularity. So when looking at this particular dashboard, right, we're saying based on every hour, index the features that flood. So you'll see here, this yellow county, 5% of the buildings are flooding every hour. That's definitely not correct. But what we can do with a long pattern of how the model performs is start to correct the hydrologic reference patterns that these particular features exist at. So if we know a building is flooded every single hour, we can adjust the hand value. We can adjust the way the stream flows are coming in. We can adjust a number of things to fine tune how these features are reacting to a particular model. Further, as we're collecting this data and figuring out what types of features might flood, what types of features are persistently flooding in cases of events like particular rainfall events or stream flow events, how are patterns and different things actually playing out on the landscape? There's a lot of opportunity for reducing some of the friction and how all these data flow together through machine learning and artificial intelligence approaches. Another thing we're excited about is how do we create forecast models. I've hinted a few times that you could take any local SWIM model, say Cincinnati or Fort Collins or Boulder, have a SWIM model or a HEC-RAS model that they've developed that has infrastructure built in, pipelines, all these other things. We can actually find a way to take those models and turn them into forecasting models and use them directly within ERMI. So to facilitate this, we built out a few different products, one of them being a cloud-based precipitation and a cloud-based streamflow warehouse that can be used directly to turn any existing water model or any existing model into forecasting. So the idea here would be, say you have a SWIM model in Cincinnati, you know it works really well, it's been tested for a few probabilistic events. You can instead take that model, interface it with the rainfall precipitation warehouse that we have, run that swim model in real time, utilize a hydrologic reference pattern that tells us how ERMI features interact with the outputs of that particular swim model, condense that to a set of directions, and then anytime anybody wants to know about flooding at that particular point, you have an access pattern or a reference pattern to swim output, as well as to national water model output in a way that is performant enough to get information in a timely way. So right now, what we have on the right to kind of close this out is we have this ERMI inventory. And the ERMI inventory comes from OpenStreetMap, OpenAddress, Microsoft Buildings, Department of Transportation Bridges, EPA underground storage tanks. And we've reduced this to a singular and standardized set of ERMI features or the urban inventory that we know how to interact with different models. Once we have a hydrologic reference pattern for ERMI, we can associate it with different types of models. The easy pickings right away was Office of Water Prediction's National Water Model. Utilizing the Oak Ridge hand layers, we were able to identify an access pattern that worked well for the entirety of CUAHSI. Based on what we learned by developing this and kind of watching it over time and watching the patterns, we were able to figure out where this method was performing poorly and different ways that we could improve it. And for that, we improved the rating curves, provided some probabilities, provided different access patterns for getting that data. Because each individual ERMI feature is also stored with respect to the FIP codes, a very standard way across, I guess, data science practices to access data, we can connect each ERMI feature directly to things like Google's data commons or the US Census. And this allows us to start asking questions about particular tracts or neighborhoods. We can say, how many buildings in this particular county are flooded and how many people lived there in 2020 and how many of those people commuted by car. That is a direct query that we can make from ERMI through the FIP codes to data commons, through ERMI to the real-time flood forecast. National Water Model is a CUAHSI scale platform, right? It doesn't perform well in some places, performs well in others. As we start to integrate with different people and different agencies, we will start to be able to take localized models such as HEC-RAS and SWIM, build hydrologic reference patterns for them. And then not only are we set on National Water Model, but we have this local information as well. We are looking forward to some community integration, right? Kyle on to talked a few weeks ago about the work they're doing with GeoConnects, building persistent identifiers that can be linked to different spatial aggregate units. For example, here you can see that GeoConnects has a particular entity and landing page focused on this particular county. I think this is Larimer County in Colorado. You know certain things about it, you can access it, and we can leverage this persistent identifier as a way to index the points and ERMI features as a whole. So anytime someone lands on this GeoConnects page, they can understand that ERMI has knowledge of the buildings and the underground storage tanks and the different hydrologic access patterns in that county. Further, we can connect to things like Google Data Commons. Here's one that, they've had a count of flash flood events from 98 to 2021, based again on the county. So when we talk about Larimer County, we not only can aggregate how many buildings are forecasted to be flooded right now, but we can look at a historic record about how many flash flood events have occurred in that county. And we connect things like Census Reporter. Simply by appending the URL to the FIP codes within them, we can connect ERMI points out to different sorts of information. I'm not sure where these are going to be useful, if they're going to be useful, but the ability to start connecting kind of the social to the physical to the network data, I think provides a lot of opportunity for both planning and immediate emergency response type situations. And so the final takeaway of why I think this approach is pretty cool is that it allows hydrologists to keep building models, right? Hydrologists love to build models, they love to improve them, make sure we're getting the best possible results for them. Google can keep indexing data, right? It can build Google Data Commons, it can build these landing pages, it can find GeoConnects PID server, it can do all these things. Google can connect data. We just need to make sure that we're using persistent identifiers that Google tends to understand. Open data efforts like Microsoft's planetary efforts, OpenStreetMap, OpenAddress can continue to improve resources and the quality of the data that they're using. Same thing with National Inventory of Dams, Department of Transportation's National Bridge Inventory. And data scientists can keep building dashboards. We're not going to try to take their role of building the dashboards. We're going to allow them to build the dashboards that meet their particular needs. But on top of all this, we have UFO CAN. UFO CAN is going to watch these different things in cloud space, right? Anytime OpenStreetMap updates one of their packages for a particular county, ERMI is going to update accordingly. Anytime Microsoft puts out new building footprints, ERMI will update accordingly. And with the reference patterns, it'll always have access to the best possible forecasts. So as models improve, ERMI will, or UFOCAN will improve. As open data efforts improve, UFOCAN will improve. As UFOCAN gets more buy-in, people might develop hydrologic reference patterns for different types of models. That'll open the doors to more forecast capabilities based on different models in different locations. And I think that's largely what I've got. Hope it was of some interest. I hope we get some time for some questions. If you have any particular questions that you don't want to ask today or come up later, feel free to email me. And then I'd like to give special thanks to Lilith. She's the PI on the UFOCAN project. Justin Singh, Computer Whiz, University of California, Santa Barbara. Kyle and Dave, who talked previously, who had pulled things directly from their materials. So I just want to make sure that they're referenced there. But that's what I've got. Hopefully it was of interest.
Thank you, Mike. That was excellent and very interesting. We don't have any question yet in Q&A. We'll wait for a bit. Yeah. So let me start with my questions then. Yeah. So you talked about the URMI inventory and how once the new features come in from different sources, you integrate them. How difficult is that, and what is the timeline that we are seeing here?
Once the patterns are established, ERMI can update in a day. The biggest thing is building out the code base that says, we're going to integrate OpenStreetMap and open address in this particular way, and these are the rules that we're following. But in terms of actually updating ERMI itself, it's really quick. And AWS is impressive in that you can watch we are never going to update CONUS at once. It'll watch each particular county and say, if there's a change in Larimer County, we're only going to update the builds for that particular county. Or if there's a change in North Carolina, the entire state, then we're only going to update the builds for those features that are changed within North Carolina.
I see. And thanks for connecting this with other talks. It was really nice to see how the flow of work is going.
Yeah, no, and I think it's really cool that all of these things are coming together in a very cool way.
Yep. We have one question. Yes, it was super interesting. Is URMI data and API available already? Can you share the link? And secondly, how are the parameters of the NWM adjusted or known? Is it fixed? And how does the user run or can change the model? And number three, can a person add an URMI feature? Is the underlying data ground truth, particularly for open source, which may have selection bias?
Yeah, so I'll try to, unfortunately I can see it, so I'll try to answer them in order. ERMI data and API will be coming soon. We are figuring out the best way to make that Amazon bucket public without potentially costing a huge amount. But the idea would be, once it's public, there'll be both Parquet and GeoPackage representations. You can access GeoPackage through GDAL directly, and the Parquet files either through Arrow or S3 Select. So I'm not sure what the form of our API is going to take, but the data will be public in the near future. Two, how are the parameters? We are not adjusting any national water model parameters themselves within the model. We are just adjusting the rating curves in the way that we're interpreting the data. A project that you will probably be interested in, if those are questions of interest, is the NextGen project. It's NOAA's effort to modularize catchment level national water model output. So you can have a different catchment and say we want to run CFE on this catchment, and we might want to run top model on this catchment, and we might want to run a machine learning with long-term or long short-term memory model on this catchment, and they'll all integrate together through the basic model interface. And most of those repos are all open on the OWP next-gen page. So if you have questions about the catchment, deriving catchments and building out the catchments that will underlie that, I can answer that. That's work I've been working on, but if you're interested in the particular parameters of those models, I would look at the CFE and the top model repos and how they're controlled there. And then
Right.
3, can a person, oh, yeah.
Yeah, go ahead. Can a person add any UMI feature?
Yes.
Yeah.
Not right now, but certainly that's going to be something we're interested in. As far as the open source and the selection bias, buildings are the one in particular here where we've got 2 very distinct data sets, OpenStreetMap, which requires users to go in and digitize these features and submit it to some community that either approves it or doesn't approve it. OpenStreetMap has a large selection bias. So when we looked at that image of Wilmington, right, the city center around the university and the downtown area was really well digitized. But as soon as you went out of that and started seeing those red points, there was no representation. So in those cases, we're using the Microsoft building footprints, which use 30 years of aerial imagery, I think, to detect these building images or these building footprints. And so we have different metrics on how we tend to prioritize data from different data sets, but we try our best to make sure that at least things are caught in those global scale analyses.
We have another question here. What is the flood forecast information provided? Is it a flood depth for the feature or just yes or no if it's flooded? And how do you know the feature elevation? Is that coming from the open source data?
Yep. Yeah. The flood forecast information provided, this kind of goes back to how you want to put together the different features. So we're providing an ability to get different information, but ultimately you could choose as you're putting together these directions to get the flood elevation. You could use the probabilistic rating curve to figure out what's the probability of that elevation. You could just choose a binary yes or no, but it largely goes back to how you're going to put together that code snippet to pull the information that you're interested in. It does have the ability to provide probabilistic depths at a particular feature. The feature elevations are coming from the Oak Ridge hand data set, so the Continental flood inundation mapping 2.0 data set, and that's all available on an FTP server through them. I think if you Google CFIM, it should pop up.
Let's wait a bit if we have any other question. Okay, then. Thank you again, Mike, for that really interesting talk. Yes, very good. And all of you, please join us for our next part of the seminar series. We will have a panel discussion next week. Oh, we have another thing. Are the IKEA instructions all code snippets? That's a...
They will be, yeah. So once, I think we're still very much in development. A few days ago, ERMI is built out for CONUS and it's connected to National Water Model through their appropriate hydrologic reference. If anybody has any opinions on this, it'd be great to hear them, but we're kind of at a point of, do we provide an API? Do we provide open-in or kind of non-authenticated S3 buckets? People can build their own. Do we provide a landing page that has the IKEA code snippets? We're a little up in the air on what the next steps will be. So if anybody has any opinions, they would be taken into great consideration.
Okay. If we don't have any other last question, I'll thank you again, Mike, and thank you, everyone. Okay, and see you all next week for our panel discussion. Thank you.
Okay.
Yeah.